So what we say, that is when a current is flowing or when a circuit is consisting of a resistance of an inductance or an capacitance only, we term that circuit or the current that is flowing through the elements, we term that current as wattless current. Why wattless current? Because the total power consumption is equal to zero, is equal to zero. So this was the basis of this entire RLC circuits, AC circuits. So today we will go through an important topic, that is your resonance, and how you design designing of filters from resonance. So this is what we are going to study today. Okay. So just let's start off with what is resonance.
Sir,
Yes.
Sir Shubhajit sir told me to inform you that sir has received all the articles for the magazine except of Shubham Roy and Shubhadeep Hajra.
You have created the groups, right, for your project.
Sir, this is for the magazine
Yes,
articles.
yes, yes. That I know. Okay, that is fine.
Yes, sir.
Shubhajit said
Sir
just
just
had
told
a
me to
talk with.
inform you.
Yes.
Yes, sir. Sir just told me to inform you that.
Poster purpose, there is a poster competition. So Shubhajit sir just texted me last night. So I thought of just informing you after the class. So I'm just informing it right now. So all the group members, the way you have formed the groups, there is a Google form attached in the Google Classroom. You have seen the classroom that has been made for the poster competition. So please, team wise, you fill up that Google form. Team wise, you fill up that Google form. Okay. See, there it has been mentioned the group members, the group member email IDs, like this you will find in that Google Classroom form. So please fill up that form accordingly and do it by today
Yes, sir.
itself.
They have filled it up.
Okay, they have filled it up, right? Okay. 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 So just let's start with resonance circuits. Okay? So what we are doing is resonance in AC, resonance and filters. So we will talk about this thing. Okay. So first, let us see what happens in case of a simple RL circuit. Let us say what happens in case of an RL series circuit. So how does a RL series circuit look like? Let's say we have an AC source here, and here there will be a resistance, right, and here will be an inductance, and this is how an simple RL circuit looks like. Let us say this is V, this is R, and this is L. So if you draw the phasors, so how will the phasor look like? This you have already done previously, I think. So the resistance, this will be in phase with your voltage, and what will happen? Current across the inductance, the current across the resistance is in phase with the voltage, and the current across the inductance, this is lagging the voltage by an angle of 90 degree. So how does the curve look like? Okay, how does the curve look like? So let's say for a series circuit, this current will remain same, I remains same across R and L. Okay, so if you are drawing the phasor, but what differs? Let's say this is the voltage across R is VR and the voltage across inductance is VL. So if you draw the phasor, say if this is your VR, okay, then this will be your current, that is I. Okay, and this will be, because voltage across the inductor leads the current by an angle of 90 degree, this will be your VL. So this is the resultant voltage phasor. So if you are asked to draw the phasor for an RL series circuit, this is VR, this is I and VR will be in phase with each other, while I will be lagging VL by an angle of 90 degree. So the resultant voltage is V, which is the vector addition of VR and VL. Okay. Now next, let's move to RC series circuit. You will understand why I am saying this little bit later. Let's do this. So let's say this is your current I, this is your resistance R, this is your, sorry, this will be a capacitance. Okay, this will be the capacitance. Let's say you can do this, draw it like this, or this is the voltage and this is the capacitance. So let's again draw this. So this is your VR. Okay, this is your same phase, that is I. Now for the capacitance, you have learned that current is leading the voltage of the capacitance by an angle of 90 degree. So this will be your capacitive voltage, which is equal to VC. This is your capacitive voltage, which is equal to VC, right? So this is in case of an RC circuit. This is in case of an RC circuit. Resultant, what is the resultant? So the resultant is, the resultant voltage is this one. The resultant voltage is this one. So in case of an RC series circuit, this is your theta, this is your V, and this is VR. Okay, and this is V. This is V. So you see here V is lagging behind I by an angle less than 90 degree, by theta, which is less than 90 degree. And here V, so remove this, V is leading the current I, the resultant voltage V is current leading the current I by theta, which is less than 90 degree. So this is for inductive circuit, this is for capacitive circuit. Now from this, if you draw the impedance triangle, so what will be the impedance triangle look like? So for this, see, this is your resistance, this is your resistance, this is your capacitive reactance, and this will be your Z. This will be your Z. So your Z will be equal to root over R square plus XC square. Here similarly, if you draw this will be R, this will be XL, R, XL, and this is Z. So here Z will be equal to root over R square plus XL square. Okay, so these are the two things that forms the basis for the next that we are going to, that is the RLC series circuit. So when I am talking about resonance, I am talking about two things. One is series resonance, another is parallel resonance, right? So we are talking about two things. One is series resonance, one is parallel resonance. Now when I am talking about series resonance, I am talking about a circuit which is consisting of your R, your L, and your C. When I am talking about series resonance, I am talking about a circuit that is consisting of R, that is consisting of L, that is consisting of C. So just let's first draw the circuit. Okay. So you know, For series, when I am talking about series connection, there will be a single configuration only. When I am talking about a series configuration, there will be a single configuration only, where the R, L and C all will be in the same branch, placed one after the other. This is your RLC series configuration, right? So what does the circuit look like? Your circuit will look like, say this is your source voltage, this is your resistance, then you have a inductance, and then you have the capacitance. So this is what your circuit will look like. So this is R, this is L, this is C, and this is your I, and let's say this is the current V, which is equal to Vm sine omega t. Okay. Now, as we have drawn the phasor like the previous cases, we will draw the phasor here as well. So if we draw the phasor, you can understand why does that particular expression for impedance comes up. Okay. So what we are doing, what we are suggesting is, first we draw the circuit. Okay. So let's say this is your VR. Okay. And this is your current I. So the current will be same across all this. The current will be same. The current will be same. Okay. Now VL is leading I. VL is leading VL. Right? VC is lagging behind I. So this will be your VC. Then what will be the resultant? What will be the resultant, you tell me? Let's say VL is greater than VC. Let's see. Okay. So if you reverse this direction, if you reverse the direction of VC, here it will become up to this, say, minus VC. What will it become? It will become minus VC if you reverse the direction of VL. So the circuit, so your VC has been reversed. So what will be the phasor look like, you say? So this will become, this part up to this part will become VL minus of VC. This part will become VL minus of VC. Now if you draw this, V, your V will be equal to VR square plus, that is V square will be equal to VR square minus. Okay, this is in case of VL greater than VC. Now, if VC was greater than VL, if VC was greater than VL, so for VC greater than VL, what would have been the circuit looking like? So here, this would have come at up to this would have become VC minus VL. So here you would have had the resultant as V dash. So if the circuit is in capacitive nature or if the circuit is in inductive nature, that depends upon whether VL is greater than VC or VC is greater than VL. VL is greater than VC or VC is greater than VL. Now if I just jot down, so your VR will be equals to I into R, VL will be equal to I into XL, and VC will be equal to I into XC. I into XC. Right? Is this okay? So we are replacing here. So this is, we are writing this as V is equal to square root of IR whole square plus IXL minus IXC whole square. We are writing this as like this. So what it is becoming? This is becoming I square R square plus I square is common. So this is XL minus XC whole square. I square R square plus I square into XL minus XC whole square. Right? Right? Okay. So you are left with R square plus XL minus XC whole entire term as Z. So while Z, this Z is the impedance of the circuit. This Z is the impedance of the circuit. Okay. So what is Z equal to? Your Z is equal to R square plus XL minus. So we can represent this as simple X. So X is nothing but the net reactance. X is nothing but the net reactance, which we write as mod of XL minus XC. Why we are writing mod? Because XC can be greater than XL or XL can be greater than XC. So we are writing the net reactance as mod of XL minus XC. Okay? Right. So what is XL and what is XC? What is XL and what is XC? XL is equal to 2 pi F into L. That is, it is known as the inductive reactance. Okay? And XC, this is equal to 1 by 2 pi FC, which is the inductive capacitance. Sorry. This is the capacitive reactance. Capacitive reactance. Okay? Is this okay? So you can get here from this that XL is directly proportional to F. As your frequency increases, XL increases, and XC, this is inversely proportional to F. So as the frequency will go on increasing, your XL will go on increasing and XC will decrease. As the frequency is increasing, inductive reactance increases, but inductive capacitance decreases. Inductive capacitance decreases. So this is the concept of RLC series circuit. This is the concept of RLC series circuit. So just tell me up till this if it is okay or not. Is this okay up till this?
Yes, sir.
Okay. So next we move on to, so we are just moving on to the next thing, that is we will just summarize this part. Okay, we will summarize this part and we will just go into the concept of what happens if XC is less than X and XL is greater than XC. So just look at this presentation. Okay. So this was what I was talking about, that when a circuit is consistent, the reactance of each tend to cancel each other. This is the thing that I was suggesting. Okay. When a circuit is consisting of an inductor and capacitor in series, the reaction of each tends to cancel each other. So the total reactance is given by X total, okay, This is given by minus XC. So what is the Z total impedance? This is equal to R square plus X total whole square. Okay. Now why we are writing this? Why we are writing this? Because from this expression itself, you can understand that if this is your X total, okay, then this will be your impedance Z. This will be your impedance Z. This is from your, because you know that the resistive current and resistive voltage are in phase with each other, and the inductance, that is the reactance, differs in phase with the current. So your R will be in the direction of the voltage, will be in the direction of the current, and the X total, that is the reactance, will differ in phase with the current. The phase angle, if you are writing this as the phase angle, then theta is equal to tan inverse X total by R. Theta is equal to tan inverse X total by R, and we suggest this as the phase angle. We suggest this as the phase angle. Okay, so this was what I was talking about. This is your circuit. This is the supply voltage. You are having resistance, inductance, and capacitance in series. Now next, I already talked with you how does XL and XC vary with frequency. With frequency. Okay, so let's say, just a minute, hold on. That's it. হ্যাঁ হ্যাঁ, আমি আপনাকে বললাম না কালকে ওই যে চাইছিলাম র্যাঙ্কটা। আচ্ছা আচ্ছা, ঠিক আছে, আমি ক্লাসটা নিয়ে নিই তারপরে যাই তাহলে। ঠিক আছে। Okay, so as I was saying, so let's see how does the circuit vary. So this is this curve. Okay, this curve is the curve for the inductive capacitive reactance. Okay, so this is the curve for the, so as I said, the capacitive reactance will vary with the frequency. The capacitive reactance decreases with increase in frequency. This I said that Xc is inversely proportional to 1 by F, and this is XL. XL is directly proportional to 1 by F, or XL is directly proportional to F. XL is directly proportional to F. So as the frequency is increasing, the inductive reactance is increasing, and the inductive capacitive reactance is decreasing. This is the nature of the curves. Please everybody note this down. This is the nature of the curve, because this comes as your 2 marks question, that plot the graph of react between reactance and frequency for capacitive reactance and inductive reactance, right? So now next is this point. Look at this point. Look at this encircled point. This point is the point of series resonance. This point is the point of series resonance. So what happens in case of series resonance? At that particular frequency, your Xc is equal to XL, and the circuit is suggested to be at series resonance. So at that particular point, your Xc and XL, these two are equal. So when the resonant frequency or the circuit frequency is circuit is predominantly capacitive in nature. Please note it down. When the frequency is below the series resonance, the circuit is capacitive in nature, right? When the frequency is below the resonant frequency, the circuit is capacitive in nature, and above the resonant frequency, the circuit is inductive in nature. This one. Okay. Above the resonant frequency, Xc greater than XL, so it is capacitive in nature. Above the resonant frequency, XL greater than Xc, so therefore it is inductive in nature. Okay. So this is an example of how you can calculate the inductance. So let's say you are given XL as 2 kilo ohm, Xc as 5 kilo ohm. So when you express inductance and capacitance in form of reactance, it will be in form of ohms, right? So what did I say? This is mod of XL minus Xc. I said initially. Here Xc is greater than XL. So your X total will be XL minus Xc. So it is 2 minus 5 as 3 kilo ohm. And you can calculate the Z total from this, and theta is equals to tan inverse X total, that is tan inverse 3 kilo ohm by 1 kilo ohm, that is equal to 71.6 degree. This is a very basic sum how to calculate the phase angle and the total impedance. So as you can see, what are you seeing here? The important part is here. The important part is here. Okay, this is the important part. See, Xc was greater than XL. You have to, when you are given the problems, you have to comment on the nature of the circuit as well. So when you are writing the nature of the circuit, or when you are writing or commenting on the nature of the circuit, your Xc is greater than XL. So when Xc is greater than XL, the circuit will be capacitive in nature. The circuit will be capacitive in nature. Okay, because Xc is greater than XL, so therefore the current is leading the voltage by an angle of 71.6 degree. The current is leading the voltage by an angle of 71.6 degree. You have to write this. Yeah, if you are asked to draw the phasor, you have to draw the phasor accordingly. So what will be the phasor looking like here? So if you are drawing the phasor here, see
Sir, can you show the graph again?
the previous graph.
Yes, sir.
Yeah, sure. This one.
Yes, sir.
Just note it down. This is the plotting of the reactance and the frequency.
Yes, sir, done.
So as I was saying, so when you are writing this, so when you are asked to draw the phasor from such a circuit, so you can draw this accordingly. So you see Xc is greater than XL. So when you are drawing this circuit, say, so this is your VR, this is your I, right? This first draw normal VL, and this is VC. Okay, but you see VC is greater than VL as XC is greater than XL. So the resultant will be, this is the resultant graph. This is the resultant graph. This is your V. Okay, and this angle is equal to 71.6 degree. So this should be the phasor diagram for this particular circuit. This is the phasor diagram for this particular circuit. So you can be given a circuit, you have to draw that particular circuit, the phase angle for that particular circuit, and you have to find out what is the value. Okay. So this is the example of an impedance of a series RLC circuit. Now here it was given as XL and XC. For the next problem you see, for this problem number 2 you see your L and C. If you look at this, L and C are given as values. Okay, L and C are given as values. So what you have to do? you first calculate XL, you then calculate XC, and here also you see XL, right? XC is greater than XL. Note down the frequency. Your frequency is 100 kilohertz. Okay, so you have calculated this. You know the X total, and similarly you calculate the impedance and the phase angle. Okay, now see, depending on the frequency, so depending on this frequency of 100 kilohertz, of this 100 kilohertz, XC was greater than XL. So the circuit will appear to be capacitive in nature. The circuit will appear to be capacitive in nature because your XC is greater than XL. So this is the graph, this is the point, this is XC, this is XL. Okay, this is the resonant frequency at this point, and the frequency is less than resonant frequency. So you can understand this, that the frequency is less than resonant frequency. Why? Because your XC is greater than XL. XC is greater than XL at the condition when the frequency is less than resonant frequency. So if you are plotting XC, this is your XL. So if this is your resonant frequency, the curve will be somewhat, or the frequency mark will be somewhere less than the resonant frequency, right? Increasing this, so it's a problem, it's a typing mistake here. So this will be 400 kilohertz actually. So we have increased the frequency to 400 kilohertz. So when your F has increased, your XL will increase and your XC will decrease, right? This you have already studied. So initially in this problem, in the previous inductance and capacitance, the frequency was 100 kilohertz. Here we take the frequency as 400 kilohertz. We take the frequency as 400 kilohertz. That is, we have increased the frequency 4 times. Okay, so as we increase the frequency, please note it down that XC now becomes less than XL. XC has become less than XL. Can you see? We have just increased the frequency. So the change in the frequency has brought about this. So actually your inductance is increasing, your capacitance is decreasing. So there will be a point intermediate where the values of the inductance and the capacitance will be, that is the inductive reactance and the capacitive reactance will be same. So with the frequency, as your inductive reactance is increasing and your capacitive reactance is decreasing, there will be a particular point where the inductive reactance and the capacitive reactance will coincide for a particular frequency. So that frequency where XL is becoming equal to XC, that particular frequency is named as the resonant frequency, or you can say the series resonant frequency. So here is again 630. You calculate Z, the circuit has now become inductive in nature. The circuit has now become inductive in nature. So where will be the frequency plotted? The frequency will be plotted somewhere in this point. Okay, this will be plotted somewhere in this point. Here you see inductance greater than capacitance. Here capacitance is less than inductance, and this is the resonant frequency. So as XL has become greater than XC, XL has become greater than XC. So the frequency, this frequency F will be greater than the resonant frequency FR. If this is your resonant frequency FR, then F will be greater than FR because your inductive reactance has become greater than the capacitive reactance, right? Okay, so I think this portion is clear up till now. Anybody is having any question? about this frequency curves? Anybody is having any questions about this frequency curves? Hello?
No, sir, no doubt.
Dimban, is the voice breaking again now? Okay. So, okay. So next what we do, we talk about the voltages in the series RLC circuit. We are talking about the voltages in the series RLC circuit. So let's say this is the inductive voltage, okay, and this is your capacitive voltage, okay. So these are your RLC components which add up to form the source voltage. And if you follow the KVL rule, the voltage will break over the individual components of resistance. VL and VC, these are the voltages across the inductance and the capacitance. Okay, and they will be in opposite phase to each other, because you see VL is leading I by an angle of 90 degree. VL is leading I. If you draw the circuit, again I am drawing this. Okay, this is VR, this is I. Okay, so VR, I, VL and VC. So if you look at the VL and VC phasors, just look at the VL and VC phasors. The VL and the VC phasors, okay, they are 180 degree to each other. They are 180 degree to each other due to the L and the C. Okay, so when you're adding this, that is VC is less than VL. Let's say VC is less than VL, then the green curve that is shown, the curve is actually the resultant voltage curve of the circuit. If VL is the curve of the voltage for the inductance, VC is the curve of the voltage for the capacitance, then the V curve is the resultant curve between VC and VL. V curve is the resultant curve between VC and VL. Okay? So, what will you say? This circuit is an inductive circuit. So, its frequency will be higher than the resonant frequency, because the total voltage, that is the resultant voltage between VL and VC, is, that is VL is greater than VC. So, what happens at series resonance? So, at series resonance, the voltage across the inductor and the voltage across the capacitor, these two are same. At series resonance, the voltage across the capacitor and the voltage across the inductor, these two are same. Similarly, the inductive reactance and the capacitive reactance, these two are also same. The inductive capacitance and the capacitive inductive reactance and the capacitive reactance, these two are also same. So you can say, so this is the concept. Xc is equal to XL at resonance. IXc is equal to IXL, therefore capacitor. So the VC and VL will be equal. But there is a but here. What is the but? that VL and VC are in opposite phase to each other. So the net voltage VL minus VC, the net voltage VL minus VC, this will be equal to 0. VL minus VC, which will be equal to 0. Okay. So if you draw the circuit, see the curve that starts from the upper loop is the inductive voltage, the curve that starts from the lower loop is the capacitive voltage, and the resultant voltage is the green line. The resultant voltage is the green line, which is equal to 0, which is actually VL minus VC. The resultant voltage is the green line, that is VL minus VC. Okay, the algebraic sum is 0. Okay, so this is the curve for the series resonance, or the voltages at series resonance. Now, what is the formula for finding out the resonant frequency? What is the formula for finding out the resonant frequency? See, Xc is greater than equal to XL. So, I'm writing this down. So this is the thing. So as for resonance, what we are saying? We are saying Xc will be equal to XL. We are saying Xc will be equal to XL. So 1 by omega C, that is in the capacitive reactance, will be equal to inductive reactance. So 1 by omega C will be equal to omega N. So omega square will be equal to 1 by LC. So omega is equal to 1 by root over LC. That is, the resonant frequency is coming out to be 1 by 2 pi root
So
over
your voice is
LC.
breaking.
Yes? Hello? Hello? Was anybody asking? Hello? Hello? Anybody? Any query from anybody? Okay. So just let's move back. So if I am drawing, so if you are given a resonant frequency, if you are given a circuit like this, if you are asked to find out the resonant frequency, you find out simply by over LC, and you see the resonant frequency is coming out to be 196 kilohertz. So that is why this particular circuit acted like an capacitive circuit. When you took the frequency as 400 kilohertz, this circuit acted like an inductive circuit. So the resonant frequency is equal to 196 kilohertz. Okay, so ideally at the resonance, the sum of VL and VC is equal to 0. So what will be the value of the voltage across the resistance? The voltage will be equal to the source voltage. See, look at this, look at this. As your V across this is equal to 0, as VL minus VC is equal to 0, as the V is completely equal to 0, so the voltage across the resistance VR, this will be equal to the source voltage Vs. Right? This is by the KVL law. So if you are asked what is the VR at resonance, this will be equal to the source voltage, that is 5 VRMS. Right? General shape of the impedance versus frequency curve. So you already have studied about the XL and XC curve, right? Here, please add to that curve this impedance characteristics. add to that curve this impedance characteristics. Okay, so when I'm adding this impedance characteristics, you can see at this particular point the impedance is minimum, and this with the resonant frequency. So resonance at resonance Z and is equal to R. So this is the point. This is the point where Z is minimum and Z is equal to R. Okay. So notice that at the resonant frequency, the circuit is resistive and Z is equal to R. See, this is the resonant frequency, and this point is termed as the series resonance. Okay. What are the concepts of series resonance? These are the points. Please note it down. If you are asked to highlight the important points for series resonance, these are the important points of series resonance. First, capacitive and inductive reactances are equal. This is the very first point. The capacitive and the inductive reactances are equal. Number two, the total impedance is minimum and is resistive. The total impedance is minimum and is resistive. Third, the current is maximum. Why is
Sir, can you
current
go a
maximum?
bit slow?
Yes,
Sir, can you just go a bit slow?
yes. See, what are the important characteristics for series resonance? The first thing is the capacitive and the inductive reactances are equal, right? So this is becoming XL is equal to XC. This point indicates to this. Next, Z, you write this as R square plus XL minus XC whole square. So this part will be equal to 0. So your Z will become equal to R. So this is what it has been written, that this is minimum and equal to R, because this term will have the minimum value as 0. This term will have the minimum value as 0. So when this is 0, then Z will be equal to R. So the total impedance is minimum and is resistive. Next, it is said that the what is current? Current is equal to V by Z. Okay. So if your Z is minimum, if Z is minimum, I and Z are inversely proportional. So when Z has gone down to the minimum point, your I will reach the maximum point. Okay. Next, the phase angle between Vs and Is is 0. This is important. See, what was your impedance triangle? What was your impedance triangle? Impedance triangle was, this was your R, this was your X, this was your Z, right? Right? Okay. Now what was tan theta? Tan theta was equal to X by R. That is, the phase angle was equal to tan inverse X by R. Now this X is equal to 0 now. So what is your theta? So this value is 0. So this is, okay. So the phase angle is equal to 0. Right? Next, the resonant frequency is given by this formula, that is Fr equals to 1 by 2 pi root over LC. Okay, one more thing I will write here, one more concept, and we will stop there. What is power factor? What is power factor? Okay, so the power factor is given by cos theta. Power factor, you know, this power factor thing you have already studied. So power factor is equal to R by Z. Okay, so at resonance condition, the total impedance is equal to R, that is your Z is equal to R. So what will be your cos theta? Cos theta will be equal to R divided by R, that is equal to 1. So the power factor of the circuit at resonance is equal to 1. Power factor of the circuit at resonance is equal to 1. So this is all about series resonance. So you have to, if you are given or if you are asked to write down the characteristics of series resonance, you have to give all these points. You have to give all these points. If you are asked what are the characteristics of the circuit at series resonance, these are the points that you have to write. Okay, this questions for your paper. So you have to write this, that for series resonance, these are the 6 conditions. Reactance is equal, impedance minimum and resistive, current maximum, phase angle 0, power factor 1, and resonant frequency is given by 1 by 2 pi root over LC. Right? Any questions till now? Or we will stop here. We will again start off with the next class at 2:10. Any questions, anybody? Kritika, Priyanshu, Shreyoshi, anybody, any questions?
No, sir.
Okay. So I think this series resonance is okay for everybody. So then we stop here. We will start off with the bandwidth and the series filters in the next class from 2:10. So just give the attendance. I will just take the attendance, just a minute. Okay. So just give the attendance.